Hello, everyone. We're recording. Okay, so welcome to this is week 3, right? So we had a break last week, but this is week 3. So we're gonna do several things today. We're gonna start with LLMs, right? So large language models, um, and that's like an advanced topic, right? But the way that I'm starting with it is essentially what I call baby GPT. So it's a much compressed or summarized version of it that I think it's, easier to grasp. And then from there, we're going to uh, add to it. Does that make sense? So that's essentially the idea, guys. And then any questions? And then we're going to look at this also is part of tensor operations, right? So we're going to kind of look at those essential ideas. Okay. All right. So you guys are section 1, I believe. Um, so I'm going to go to section 1 content. So we did machine learning word problems, right? We went over that topic. And that was the last one that we looked at here. And then tensor operations is kind of the topic that we're looking at today, right? And I won't be able to cover all these problems, obviously, so you will have to do them on your own. Okay, so this is not a homework you have to submit, but I strongly recommend that you go through these. And they're essentially the code is there, it's just about repeating it. To motivate these, I'll start today with, you know, the LLM that I was talking about. So I'll put this module under, I'm going to call it baby GPT. Baby GPT. And I have the code already on the GitHub, so I'll just provide the link and my notes from there. So again, today it's not so much, don't look at it as I want to understand everything about an LLM or a transformer or right. That's not the goal. That's a process that's going to take weeks for you to actually grasp it. This is more about the operation, right? You want to understand this operation, it's going in here, the inputs are this, these are the outputs. So just kind of mechanically understand what these operations are, and eventually we're going to start to fit in the whole big picture in there. All right, so I'm going to move this module, baby GPT, to run right after tensor operations as we are covering basically both kind of together. And we're looking at it in the context of just the operations themselves. So I'm going to add the link here. So that's in my GitHub. Go to repos, and it's this one, how LLMs work. So this thing is always in the way. So I'm going to just provide this link. And the link, I'll just say code, something like that. All right. And there it is. So there's actually, so I'm gonna just try it out. Close this table of contents. So right, so you are here in these two modules, tensor operations and baby GPT. And let's start here. So I'm going to click on the code. And you can see I have some notes. So I've described these are the things that I'll talk about today. Essentially, all of it is leading up to, the LLM, how it works, some of the mechanics. And the way that you have to think of it is there's really two parts to it. One is just building the architecture, the forward architecture from input to output. That's one thing you want to understand. And then there's, of course, the training process, right? So the data goes in, compared to some real data, calculate an error or a loss, back propagate. But usually that part is really what PyTorch is for. So PyTorch does a lot of the heavy lifting for you. So really where you have to focus a lot of attention to understand the algorithm is in the architecture, right? The inference, the forward function, okay? So that's what we're going to discuss today. So yeah, so this is the code as it is. So here I have several files that are, I think, super important to understand. So this, of course, is the baby transformer code. So that's this one here. Then I have a full GPT that's fully functional. So this code that you see here, GPT Scratch Huck Finn, will be something that you will use for one of your homework assignments. Okay, so this is actually the code, but it's much, this is fully functional. And I provided a book here, Huck Finn, so you essentially can train this model on Huck Finn or way more books, right? So you can train it on as many things as you want. Remember that in this course 520, we do things from scratch. So the goal is to understand the algorithms, right? Not to build the very best GPT that you can. For that, you would start with a pre-trained model and then fine-tune it. In this course, we're doing the pre-training part, right? That's the idea. All right. And pre-training would require thousands of GPUs, all the data in the world to achieve something really good. So obviously our models are going to be less than that, right? Not as good as that. All right, so here's some background. And then these are part of tensor operations, so linear algebra, attention, and NN. So I'll go over these as time permits. This function, NN linear, X, W, and B, is essential to understand all of this, right? So these are just the building blocks of what we're doing. So essentially, this talk is really like how LLMs work, right? Under the hood. This also references a little bit more code, more complete code. I think this has tick token, etc., which we will talk about later as well. But essentially, we're going to talk about the key fundamental operation, and that I would argue, if you ask me, so what's the most important math operation in transformers or deep learning even, right? So I would say, oh, it's the dot product. And then the dot product is essentially the building block to the matrix multiplication, right? So this is the thing that we will do today. This is problem 37 of the 100 plus problems that I've given you under tensor operations that you should go through, okay? But we're going to walk through this one. So here, we'll talk about the dot product, which is this one, a little explanation of how it works. Feel free to ask questions. Then how once you understand the dot product, then the matrix multiplication and how that works, some of the intuition and meaning that you can infer from that. You have that here, matrix multiplication, why it matters, and then LLMs under the hood. So understanding this idea of the attention mechanism. And before I go into like a whole theoretical thing, right, of, all these concepts about it, we're just going to mechanically process it. And again, this is where I've explained to you many times, the key thing is those dimensions, right? So you remember if I said, when we were doing word problems, I said that what is the dimension of X? What is the dimension of Y? Remember that? So this is where that mindset becomes very important, because you have to think of it as the things that are happening in the transformer, they're in this is an example, but they're in like the fifth dimension. You can't see them really. It's too complex. So what we do is we look at a shadow of that, right? And the shadow comes in these dimensions, okay? You'll learn how to interpret the dimensions to know what's going on. And so that's how we're going to do it. And I think that's the best way. So we'll talk about what is attention, and these. And as I said, all of these things are inside the complete full-on LLM for GPTs. All right. And then we'll cover these ideas here. And then finally, we'll get to the baby transformer, GPT style from scratch. And so this is just, it should be a complete script from beginning to end of the inference process, right? And so we're going to just mechanically, this is the most simplified I could do this, right? So it's the most simplified that I can do. You can see, look at it. That's not bad, right? So some of this is library, some of this is variables, and then ChatGPT in just 20 lines of code or less. You see, obviously, for it to be more, more powerful, it needs more complexity, but this is a super summarized version of it. All right, so if a GPT has like 6 blocks, this one only has 1 block. I did little things like that to simplify. But we'll go through it. And that's kind of the end of that sequence. All right, so that's the idea. Make sense? So we're going to go through this as a complete exercise. And the code for it should be this one, baby transformer. So it should be the same thing that I'll go through. And like I said, if you want to already look at what a complete one looks like, this is the actual, you can see the code is a little bit more massive, right? So we have different sections that are happening, and this is the training process, but we'll start with simple and then build to complexity. Okay? All right, so let's get started then. I'm gonna use, so that was kind of just to give you an idea. So I'm gonna go back. Dot product is where I want to start. And I'm going to use Colab for this. New notebook. Okay, I'm going to add a few. I don't need a GPU right now. We'll be using, really just random data. As usually just like to use random data when I'm kind of figuring out the architecture. Okay. So let's take a look at the first thing. So what is the essential operation in machine learning and deep learning, and deep learning and transformers for sure, is the dot product, right? Which is the building block for the matrix multiplication. So if you think about it, the GPU was literally created to make matrix multiplications. Like it's a device, hardware, right? That does that very efficiently in parallel, performs this matrix multiplication. And the idea for it is, if you don't know this, is you probably heard that NVIDIA actually started with computer graphics, right? It was for video games, right? Not for machine learning. And it was, people have their gaming PCs or whatever that are very powerful. But the idea was that in a 3D world like this, let's say that I'm in a first-person shooter game, so I'm a mesh, right? Made up of all these vertices, points in the mesh, right? And people are playing video games, so they want to see the movement to be really fast, right? So in the past with a CPU, you can imagine that you would basically have to grab one point. Let's say that you want to take this mesh and just move it over there. So as it turns out, that's just, the mesh is just a matrix, and then you multiply it times another matrix, a rotating and rescaling matrix or something like that, and you can just move it. That's just, a matrix multiplication. It's a very common practice. So then essentially with a CPU, you would grab the mesh, and in sequence, you would like grab this point, move it over there, then this point, move it over there, then this point, move it over there. So you can imagine what would happen to the rendering. It looks like this, right? So it's rendering all down, and that was not great. So instead, with a matrix multiplication, you take all the vertices, make the multiplication, and all appear over there in parallel at the same time. Do you guys understand? So this is essentially the problem, right? That NVIDIA was trying to solve, is like, games look terrible when they're doing this. It'd be great if like they move more seamlessly. But that same operation is the same operation in machine learning where so the mesh is what? X data, right? And then what is the thing that would move the mesh to the other place? The weights. So you've made the matrix multiplication and it's equivalent to that. Okay, so that's the operation. And so that's why it was such a revolutionary thing, right? So the math was there, everything was invented. They just didn't know how to train data really quickly. Okay, and so that's where GPUs came in and do it much, much better. So this matrix multiplication that I'm talking about, just imagine is like grabbing the data, multiplying it times something in a weights matrix to transform it into the next layer, right? So that's what we're going to talk about now with the minimal operation called a dot product. So this is a dot product example in PyTorch. So this is a minimal example that demonstrates how to compute the dot product of two vectors using PyTorch. Okay, so we're just gonna copy this, put it like down here. Okay, I'm going to remember in this course I'll be using either PyTorch or NumPy, and those are essentially the libraries. There's the little check. All right, and so now I'm going to create just two vectors. I'm going to create two vectors here. Define two 1D vectors, right? So this is the idea, tensor is just a generic name from anything that's a vector, a scalar, a matrix, a 3D matrix, 4D matrix, in higher dimensions. So in this case, I have, three values in each vector. And what I want to do is I want to perform a dot product of them. And that's an operation we have to learn, right? So, but that's the great thing about, deep learning. Maybe you've heard that, linear algebra is super important, and it's true. So if you have time, I definitely encourage you to take linear algebra, but we don't need everything in linear algebra to understand deep learning. There's only a set of fundamental operations that are critical for it, right? Obviously, the more you know, the more understanding you will have. So now that I have these two vectors, we want to see, we'll perform the operation and then kind of analyze what is being done. All right, so in this case, I'm going to add this here. So I have the two vectors, A and B. These are just Python lists here, right? And I'm going to take these Python lists and I'm going to apply torch.tensor to them. And this will essentially convert the lists into PyTorch. All right, so I've done that. And now I'm going to compute the dot product of these two vectors. Okay, so I'm going to use a function called torch dot to calculate a dot product of B. Right, so we're going to perform that. So that's done. And then here we just print out the value, which is 32, as you can see. Right, and this is how it works. It's just a mechanical thing with certain rules. There's going to be certain rules about the dimensionality needs to match and everything. So now let's take a look at what this operation was actually doing. So we can take a look, go to the note, so that gave us 32. So essentially the explanation of this is that the dot product of two vectors is calculated as follows. So I'm just going to copy this and we're going to take a look at it. All right. So it says that we take, and this is obviously here as times. So 1 times 4. So essentially these vectors are of size 3. So you're going to multiply them where each cell is multiplied with the value of the corresponding cell. So 1 times 4, 2 times 5, 3 times 6, and then the result of that is added, right? And that's essentially it. There's no magic or anything like that. It's just an operation that you just kind of have to get used to, but it's a very efficient operation that then is incorporated into the matrix multiplication to essentially multiply your data with the weight matrix to produce the next layer. Okay, and this is really important because this is the neural network itself, right? So it's the input times the weight to produce the next layer, which is a hidden layer, or it could be the output layer, and so on. Okay. So I've done this operation. So you can see 1 times 4, and then 2 times 5, and then 3 times 6, and this should give us 32. And there you go. So that's 32. And that's essentially what has happened there. Make sense? Yeah. So definitely, practice the problems, the 100 plus problems. It goes into more detail about it, but this is essentially what is going on. So if I wanted to use, something like this, where I have, 4 values in the first one, but 3 in the other one, it's not going to work. All right. And this is the classic thing that you're going to get in deep learning, the classic problem when you're building some kind of architecture. You don't quite think it through, and so it breaks. But the errors are usually related to this. So you just have to understand that these dimensions need to line up. So now if I add something like 5, then it should work and just give me, but now these vectors are of size 4, which this is similar to, if you remember, like something like the iris data set, right? Where you have every sample and then it had 4 features, right? So essentially here, we're saying it has 1, 2, 3, 4 features, and the vector could be considered a sample, for instance. Okay, so I perform this operation again. And you can see the value went up to 67 because it added that additional term, which is 7 times 5, which is 35. 32 times 35 is 67. Does that make sense? So pretty simple, right? And that's it. That's like the hard part. No. But that's like the beginning of it, right? So you start to get worried about it, and it starts, but this is really it, right? So it starts with this matrix this is the dot product. This is just one vector to another vector. Now we can add a little bit more by having, instead of just one sample and one column in the weight matrix, I'm going to have more samples and more columns in the weight matrix. And then I can start to do this magical thing called the transformation. Some people also call this the projection, depending on how they're looking at it. So obviously for transformers, it's all about these transformations, okay? So that's the key underlying point. So now we are ready to move on to the next part of this. So, we're still here so we did this. So the torch dot from the library requires both inputs to be 1D vectors of the same length. And then for matrix style multiplication, we will use torch.mapmul. Or there's also like the @ sign is the same thing in PyTorch. I happen to like mapmul. That's just a preference of mine. There's no difference, really. And you'll see in the code, I think in the LLM, the operation is an @ sign instead of torch mapmul in some of the examples. And then later on, you'll see that actually torch mapmul is now abstracted, right? So really what we use to build our deep learning algorithms is something called nn.linear. nn.linear will become super familiar to you because we use it all the time. But what nn.linear does is it does like 5 lines of code in one. Like it does a lot of things behind the scenes, but I like when I started with deep learning, if you guys can believe this, in 2015, before 2015, there was no deep learning frameworks really, right? It was much harder to implement this. And then we got TensorFlow in 2015 towards the end of that year. And it was all mapmul. Like you had to code everything from scratch. You'd create the weights, the bias variables, everything, do the mapmul, all that. Today, we have nn.linear, which does all of that for you. So you don't actually create a weight matrix. You don't actually perform the mapmul. But if you want it, you can take it out. Like you can take out the weights and all of that. All right. So right now I'm just giving you the fundamental concepts, kind of going from the math to the code. And then later on, in the semester, at least in the second half of it, it'll just be nn.linear, essentially. All right. So now what am I going to do next? And this is actually pretty important and profound. It's not just a mathematical operation, but there's also very interesting meaning here, right? So we'll take a look at that. But essentially, let's just mechanically consider it, right? So here, what I did before, the dot product operation I just did a second ago when I did this was essentially just, you can see my mouse. Yeah. So it was essentially just taking this row times one of these columns. That's it. That's all I did in that dot product. And if you notice, one thing that they will have in common is that this is 4 going that way, and this is 4 going down, right? So 4 rows versus 4 columns. Those two things need to align, just like I showed you in the dot product. But the matrix multiplication, what it does is obviously now you can add more columns. So essentially, it's a transformation that you take. So think about it. In the previous example, we took this one, took 1 times another 1 and produced, I think, 67 or 32, right? And that became a new value for this, right? So, but now we can take this one again times another column of size 4, but with different values. Do you see that? So we do that, and now guess what? We get another value, maybe 55. So I can do this 6 times, 20 times, 100,000 times, whatever I want. I can't change this dimension, but I can change the number of columns I have in here. And the beauty with that is that you're transforming your sample, because now this sample that I had that had 4 features, right? And that's all the space or all the meaning that I had in it. By doing this multiplication, now if you think about it, this sample becomes a sample of 6, not a 4 anymore. And what did I do there? I transformed it. Into what? Who knows? Because the only one that knows is the AI, right? That's the thing with AI, is that AI is trying to solve a problem, classify the cat and the dog. So it takes the image and it's going to do all these transformations. Into what? Who knows? But the point is, when it gets to the last transformation, it must be a good one, because the performance is going to be good. You see that? So the performance is the one that, guides the LLM. So right now, I'm only showing you the operation, but I'm not showing you how to get these values. These values currently, if I imagine I just take random data here and random data here, I will produce the matrix in the correct size, but with random data. Do you see that? So that's why it's nice to think in random data initially, because you just build that pipeline. You know that this matrix 150, comma 4 times 4, comma 6 will give you 150, comma 6. That's key. But you know that the 150 samples you had here, now they're here, right? And they have 6 columns, but with random data. The second step is, once that architecture is built, is to do the training, right? So you give it an input, it gets to the end. That thing that's in the end is compared to some real data, take an error, back propagate, update the weights. So there's a whole thing called stochastic gradient descent that would update especially these values. So that's like the AI, right? So some famous people in AI, say that, humans are afraid of AI, that, it's going to kill us all. But really what they're afraid of is what? This file. This is what people are afraid of, right? This massive this massive file or set of files that actually define the intelligence. Do you see that? So all LLMs, Claude, ChatGPT, all of them, and Anthropic, I think Anthropic is Claude. And so all the other one is Meta's, what is it? What is Meta's? Do you guys know? I forget. Llama, there you go. Thank you. So Llama, all of them essentially do this, right? Essentially have these operations, way more complicated operations, but they all have the same architecture. But I guess their intellectual property is the weights themselves. Each one might have a slightly different set of weights. Maybe OpenAI's is a little bit more powerful, etc. Do you guys see that? So that's essentially what's going on. So hopefully you understand the mechanics of it. So we do this dot product. I showed it for one. Now you can just do it for multiple ones. And essentially that's called a matrix multiplication. So it's a way of transforming my 150 samples into still 150 samples, but where now there's additional columns, right? That actually it's like it's inferring that, for instance, I'll give you an example. You're trying to classify cats and dogs. And so here it creates this column. We don't know what it is, but it turns out that it's like the level of furriness or the level of how big the animal is. Cats are smaller than dogs, so that might be helpful, right? So it's something like that. Okay, but essentially only the machine learning algorithm figures it out because it helps it to classify the problem, and that's called a latent column, essentially. Okay. All right. So now that we've talked a little bit about the intuition, we can dive into the operation. And this will be important as we start going through because everything, as I said, is some kind of a matrix multiplication. So this minimal example demonstrates how matrix multiplication works in PyTorch using torch.mapmul, which is a foundational operation in deep learning and linear algebra. So here our objective is going to be to multiply a matrix X of shape 150, 4 with a weight matrix W of shape 4, 6. And then we will produce an output matrix Y of shape 150, 6, which is the transformed matrix. So this is in any time you see nn.linear, which is all the time, it's essentially what is happening. X, matrix multiplication W. For simplicity, I've removed the bias. There's an additional bias vector. So I removed that. But this is, called feature transformation. This is the neural network forward pass also, right? So all those is essentially getting the input and getting to next layer or the output layer. So now let's just go through it just to kind of visualize it a little bit. And then we're going to continue to build up from there. So I have enough cells so we can start here. So I'm just going to copy this. I'm going to move this down here. I already have torch invoked, so I don't need to do that. So let's just create a matrix that is, as I said, 150, 4. So what is this data set? So I like, to become familiar with certain data sets, right? Because I know everything about these data sets. So for instance, there's MNIST, there's Scifar10, there's the IRIS data set, right? So that's a nice one to understand. So the IRIS data set was, just to give you some context here, was created by Fisher, and it had 150 samples, and each sample had 4 features or columns, which were, essentially, they were looking at flowers, but it's not images. Instead, they just took flowers and took some measurements of them, 4 measurements. So that's the sepal length, the sepal width, the petal length, and the petal width, right? So like the dimensions, so imagine you take a leaf and you look at, but different parts of the flower. And just based on those dimensions, they were trying to classify the flower into one of 3 classes, which are Setosa, Virginica, and versicolor. This problem is so classic in machine learning that I actually have iris flowers in my house because of it. Right? So it's just, a nice ML thingy. All right. So you create now, the matrix 150, 4. So one key thing that I recommend strongly is because we can look at the data, right? So we can actually look at the data. If you look, that's the data that I created. Notice that I did a torch ran. So the data is just random. Usually I like to just use random data. But the thing is, okay, this is a small set and already it's not really that meaningful to look at the values in here, right? That doesn't help that much. Now imagine if I was doing, a random data set simulating MNIST, that would be 70,000 by 768, or sorry, 784. That's not actually something you can, really visualize. right? I could have done, let's say 65,000 times, or yeah, 65,000 times 784. Okay, that's random. Then I do this, but see, it's not even showing all of it. And even if it did, why would I even use it? You see that? It's pointless. So instead, what we want to do, which is a habit that you'll probably want to follow, is to just print the shape of it. So you're just going to do x dot shape. You see that? And then it gives you 150 comma 4. Let me get my PowerPoint. All right. Yeah, so we have that, matrix. Now this is the weight matrix. Okay, so this one is essentially, we perform the multiplication of this X with this W, right? To produce another set of another matrix, right? Which is now a representation of the next layer, for instance, or the output layer. Okay, so you can see that here. And we print the shape of it. So W dot shape. So you can see this one, I can print the values right now. They're kind of small. It's a kind of small matrix. These values are essentially the weights that the neural network needs to learn. That's the magic. That's like, as I said, this is the Terminator that's killing you right there. Right? So, but it has to be learned with stochastic gradient descent. But of course, right now, let's assume it's already been trained. So then what would happen is we take the data times these weights to produce the result. All right, so I'm going to do the shape, and you can see it's 4 comma 6. And now I can perform the actual matrix multiplication between these two and print the shape, which is y dot shape. And it is 150 comma 6. That is a transformation. That's where the name transformers comes from. Okay, all these and you do way more than this in an LLM, as you will see later on, but this is the fundamental underlying operation. So here, let's switch over to the whiteboard for a second. Okay, so this is the whiteboard. Okay, it's working, thankfully. All right, so as I was saying, iris, we're assuming iris data, right? So the iris data set. Iris. So we're going to play with this concept. So the iris data set has 150 samples, and it has 4 columns, which are the 4 features, F1, F2, F3, F4. And then it has the Y vector, so this is Y, this is X, as you guys know, this is 150, and this is 1, right? And the 3 classes that it has are going to be Setosa, Virginica, and versicolor, right? So the 3 different types of flowers. So what I was doing, essentially, I did this. So I did that X matrix multiply W, right? And that produced something. Let's call it for now, let's just leave it as question mark, right? So I had the dimensions 150 comma 4, and that produced 150 comma 6. Okay, so what is this equivalent to, this transformation? Well, it's actually, we're building the neural network. So when you build a neural networks, you've probably seen things like this, the architecture. We don't need to specify the number of samples in there, right? So I don't need to say that there's 150. What I do need to say is that the dimensionality of the input vector to the neural network, so this is X, so this is what? 4. So notice it corresponds to that floor. Do you guys see that? And then what I did is, and then here just one sample goes in this architecture. So then when I did this operation to convert it to 156, essentially what I did is I made a second layer of size 6. Do you guys see that? And that layer we can call a hidden layer. Okay, hidden layer. You can have hidden 1, hidden 2, hidden 3. But that transformation, what it does is it takes the data from this point to that point. And there's going to be more operations there. Like there's going to be something called a ReLU, it's dropouts and things like that. But essentially, in the most basic form, this is, it doesn't have any nonlinearities yet, but the architecture is being created. So now I pose to you the following. So if we wanted to do, we're fine with this, and we want the next layer to be the classification layer, we would essentially do a layer of 3 neurons, right? So 3 neurons means that each one of these represents C1, C2, C3. And what we would want is for this values to be like a probability distribution. So we want to produce values where if it's class C2, then this should be like 98, and this is 0.01, and this is 0.01. Do you see that? So that's essentially where we're going to, so that we can do the classification. But more importantly right now is how do we do this transformation? Do you guys see that? That's really the key thing. So now I want the samples to go from 6 to 3. Remember, it's all random data. So you just build the architecture as random. But then when you do training here on this end, and I'll use a different color, you will provide the real data. And for this sample, that flower was setosa, right? That might be the first one. So that's 1, 0, 0. That's the true data. So then in the training, what needs to happen is the model, updating all these weights, needs to learn to produce. Imagine initially it produces 0.2, 0.2, 0.2, right? For some reason. Not very helpful. But what you wanted to do is, over time, as you're training, you're changing those weight matrices, this one, W, and you want this to become something like 0.01, 0.01, 0.98. If you look, 0.90, oh, sorry, I did it wrong because this one should be, it should be 0.01, 0.98. Why? Because 0.98 is essentially 1. Make sense? So that's the other thing, right? That we will train to achieve that objective. But right now, let's even, that just says, okay, that's the class that we want. Great. But now I ask you, so what we need to do is we just need to figure out how to convert this, essentially this matrix over here, into this matrix over here. For every sample, now it's represented by 3. Do you see that? So we need to now perform a second layer over here where we get 150, 3. Do you guys see that? Where this one becomes the input to it. And then we need to create another weights matrix with another set of dimensions that produces that. And that's it. That's the whole magic of this thing, like the mechanics of it. So now let's try to do that in PyTorch. So we're going to go ahead. So, so that was kind of the illustration. So let's go to PyTorch. I'm going to share the screen. Okay. So now you guys can help me out. So now one thing, just for notation, I don't want to call that layer Y, because usually we denote Y as the final layer. So I'm going to call it hidden 1. Hidden 1. So now what do I need to do? I need to create another weight matrix, right? So I'm going to create a weight matrix like this one. You guys see that? I'm going to call this one W2 because it's a different weight matrix. And I'm going to, this is H1. So now I do H1, H1. All right. And now I create another matrix. Obviously, this one needs to have different values, right? Since my inputs are now 150, comma 6, so each one vector is 6. So I need this to be 6. Do you see that? And then this one, well, I want it to be 3 because I'm creating that last layer. So this is going to be 3. Do you see that? And so now I create this one. I'm going to perform the map mol operation. But I perform it with, instead of X, it's got to be the previous thing I produced, which is called H1. And this weight matrix should be W2. And then this is now Y. Do you guys see that? So that's essentially the whole process. So let's make sure I ran all of these. So that's H1, W2, and that's Y. So now what we do is we print the shape. So Y dot shape. And there it is, 150, comma 3. That's a neural network. All that it's missing actually is like adding a non-linear activation, which is, like a ReLU or something, which you just take some values and run them through a function. But essentially, this is a neural network. This is what you're building. And essentially also, you're doing just transformations. And that's where the name of a transformer comes from. So now, 150, comma 3, you can see that I took my data, I ran it through the architecture. Because the weights have, after training have meaning, boom, I'm able to classify. What if I want to make this a deep neural network, right? How do I do that? Well, pretty simple. Instead of calling this one Y, I'm going to call it H2. So that's a second layer now, just like that. So obviously, I want to make this, not 3 because that's the last layer. So let's go, let's be like exaggerated and do 100 neurons. That's a lot, but we're doing it. We're just adding a second layer. So now this one takes in H1, W2 to produce H2. You see that? You can see I transform all the samples to being vectors of size 100. What is that equivalent to if you do the little drawing? We go to the whiteboard. So this one here, right? Essentially what I'm doing is I'm adding here another layer in between of size 100. So that's that 100 in size layer. This is H1, this is H2, and this is finally Y. This is a deep neural network. Why is it deep? Because there's one more layer. That's it. That's the whole thing. And all of it is done through matrix multiplications. You saw me, I'm creating a W. Oh, I didn't include the bias. In PyTorch, as you start to create these things, that would make it extremely like verbose code, right? It's like, so many lines of code. So they simplified it by creating this function called NN-linear. So we'll learn how to use NN-linear in a little bit, and we will see that just, includes everything inside. So now we've done it. So we're done. I'm going to share the screen here. All right, so we completed that exercise, and we have, oh yeah, no, I haven't. So I did this 150, comma 100, so I need the last layer, right? So the last layer needs to be, let's call it W3, another set of weights, right? To go from that layer of 100 to the final layer. So this is going to be W3. What's this value here? 100. Very good. 100. What's and 3, right? And 3. And so now you have that. You perform map mol. It's going to be with H2 because it's that previous layer. The weight matrix is W3. And this is my final Y, which produces my 150, comma 3. And there you go. So now you did all these transformations, which is equivalent to going through all these layers of the neural network, and boom, you have essentially built a deep neural network without the nonlinear activation, just to keep it simple. All right, any questions on any of that? So it's like the most basic building block. There aren't like 100 building blocks. I would say there's one, and we're always doing this, there might be a few variations here and there, but essentially you're always doing this. So, because the thing is, the beauty about this is you have to think of it like this. There's always some complicated operation, algorithm thing, but very smart people can look at that and say, oh, I can convert that into matrix multiplications. Do you see what I'm saying? So if you're efficient, you can yeah, this is the algorithm, but that's too slow. It doesn't work. But actually, if I do this, here's the matrix multiplication version of that. You see that? So you can always, at least part of it, right, can be done that way. And you're improving velocity. So that's what sometimes in LLMs is hard. And advanced algorithms, the algorithm might be simple, but that set of matrix multiplications that accomplishes it is what is sometimes a little bit tricky. Okay. So that's why it's important to understand this so that when you're reading the algorithms, you get what's happening. All right. But that's something really nice. You'll always be like, and then, this is a matrix multiplication version of this idea. All right. So now that we've covered this, I think that's actually covering a lot. We did this code overview. So I'll just summarize in the notes here. So we got the shapes. As I said, I'm using iris here. Go read up Fisher's iris. Essentially, that's what I'm doing. So it's 150 samples, 4 features: petal length, petal width, sepal length, sepal width. We talked about this in the word problems. I took a transformation matrix, 4 by 6, because I explained how it needs to be, right? So the 4 is because the data has 4. That cannot be changed. And the 6 is whatever you want it to be. And actually, it ties into this question of how many neurons do I want in my layer? Everyone's always asking me, so what's the rule or what's the science? There's no science, right? It's just whatever, like a rule of thumb is funnel it if it's really big. But if like this, play with it. Doesn't make sense to have 2048 for iris, things like that. So you have to think of it that way. This is a multi-layer perceptron as is, not deep learning. And remember, it's linear because there's no, we'll see a little bit later that we do something running the data through one more function that adds something called a nonlinearity. But we'll see that later. So why it matters. So this is core to how neural networks compute outputs. A layer transforms input features into a new representation, such as a hidden layer, by multiplying by a learned weight matrix. Right? You build the architecture first. When you can actually do predictions once the architecture is done, but it's random data, so you can expect random outputs. The example is the essence of this. So this is actually now the formula. So I was just doing this. There's this component called a bias, which is, simple. We'll look at that later, but that essentially is like a linear equation, right? And you learned this, this in high school, right? So draw a line, so you have the slope and things like that. So this is essentially this example is the essence of this, and all of this is abstracted in PyTorch by the NN linear function, which maybe you've used already, or we will certainly be using this quite a bit, this semester. Okay, as it is the fundamental operation. All right, so we covered that, and then the hidden layer produces this example. All right, so great, right? So that's pretty good. So we got through this essential operation. Now we are ready, not to build the LLM yet, but to build to try to understand LLMs under the hood. So whenever you hear about LLMs, you always hear about the attention mechanism, right? So what is the attention layer? What's going on with the attention layer? It pays attention somehow, right? You've heard that expression. And so the classic example that I can give you to motivate this is, and so you have to think historically, right? So how did transformers get invented? So they got invented in 2017 by Google, and they were just trying to solve one problem, which was the translation problem. So the problem in translation is that some language will say uh, big cat, and other languages say cat big. Do you know what I mean? Like they invert the words. And so the translation could not be one word to another word. It had to take that into account. And so that was hard back then in 20, in 2015 and but that's essentially what they did. They were translating languages. They built a whole transformer for it. It had, and we'll later on look at it. The whole transformer is actually bigger than what we use for GPTs today. Like twice as big because it had an encoding layer and it had an encoder, a decoder. These had to work together. But essentially, so what they wanted to do is, they built the architecture, and in particular, they used something that already existed. Someone else had invented this called the attention mechanism, but it dealt with that problem, right? In a meaningful way. In the case of GPTs aren't always translating, right? Obviously, sometimes they're just about you communicate with them, you ask them questions, etc. So in that case, they also use the attention mechanism, but to just understand the sentence in a better way. So think about this example, right? So the word bank, right? So is it bank of the river, or is it the bank where you keep your money? So a large language model, when it looks at that sentence, it wants to understand which version of bank it's looking at. So instead of having one vector of values that represents the word bank for every context, it creates individual vectors depending on context. And so it basically pays attention to the words around it, right? So if I say the robbers went to the bank and took the money, well, the attention mechanism allows you to understand that word bank means the financial institution. But if I say something like, we were running and then I slipped and fell near the bank of the river, right? So that implies, not the financial institution, but, an incline or, a bank near a river, etc., a sandy area, something like that. So the words around it help a lot to provide context. And that is what the attention mechanism was made for. Is basically like, you'll see it's a square matrix where you have all the words, for instance, here and here, and then you just figure out which ones are related or important. But again, that's the intuition. Let's look at this mechanically, okay? So we're going to once again go through the operations, matrix multiplications, just to understand the attention mechanism. And once you know the dimensions, you can imagine what it's doing, okay? And remember, the values are random. So obviously, as it's training, the values in the attention mechanism are being updated until it's got a good set of values that give it what it needs. So that's the beauty with large language models and deep learning is that the network learns. This is how it learns on its own. All right, so this repository walks through the attention mechanism at the core of transformer models like GPTs, BERTs, Llama, etc. So I'm going to implement this from scratch. So usually when you talk about attention and you ask anyone, the first thing, one of the answers is queries, keys, and values, and this means this and this means that. And I think all of that derives from like information retrieval, etc., of how they were thinking about it. But I just think you don't need this to understand it. What you should understand is the mechanics of it, and then you will see how it works, right? Because it's very specific. You do create a Q and a K and a V, and I will create those, and I'll use the same term, but really, it's not really. I think it's, if anything, is more confusing, right? So just try it how I'm explaining it, and I think it'll make a little bit more sense. So we're going to implement these, and we're going to assume that they're going to be transformations. Transformations from what? From the original data. Okay? What is the original data in an LLM? It's going to be sentences, right? And the sentences, obviously, it doesn't understand strings. So we got to convert them into numbers somehow. For now, just random data. Okay? We're going to do the operations with random data, and then it'll take some work for us to go to sentences to the input eventually. Right? But, we'll do that later. So now let's think about this QKV. All right. So are derived from token embeddings, how dot product and this is how dot product is computed, and how causal masking could enable the autoregressive behavior, which is something else that we will talk about, which is that predicting in a sequence. All right. So here's essentially what we're going to do. I'm going to need another X, right? An input. So I'm going to simulate this. I'm going to take this now, and I'm going to move over here. And this is the fundamental tensor for you to really start to understand large language models, okay? It's a tensor of 3 dimensions. So essentially, it doesn't have just like 32 comma 40, right? Or 150 comma 4. This one has 32 comma 40, but there's an additional layer, 512. Okay, so what does this represent? And just to think about it, this is like a cube, right? So this is a cube, like a Rubik's cube or something like that. So the first values, 32, are the number of samples. Okay, so just like in our previous example, I had 150 samples. That's what this is. But when we train models, we don't train one sample at a time. You probably have heard about this. When you use a GPU, you want to be efficient. And a GPU usually, like if you're training a model to learn about cats and dogs, you don't just give it one image, you give it a batch of images, right? So in this case, think of it as giving it 32 images, or in our case, for a large language model, 32 sentences. Does that make sense? Chunk of sentences, okay? So 32. The next one here is the sequence, which basically means the sequence of, let's call it words for now, although you don't actually use words, you use something more similar to syllables. But let's say the sequence of words. So the cat is sleeping on the table. 40 of those. And it doesn't matter, if it's obviously sentences are variable length, but in GPUs and in LLMs, we don't use variable length things. Instead, we'll have 40. And if some sentences are shorter, we just ignore whatever's in there. And if some sentences are longer than 40, we truncate, right? And we lose that data. Does that make sense, guys? So essentially, if I just do 32 comma 4, I think that's understandable, right? So it's 32 sentences with at most 40 words, except that the words have to be represented by IDs. So what I mean by that is, a sentence would be the cat is sleeping, but you can't give strings to the LLM. So initially you will do a first pass where you create the vocabulary. And there's a whole, and this is really important, by the way. This is a very important step. There's an algorithm called tick token, which we will see later. That's actually what is really good. It's based on a very complicated algorithm on looking at the frequencies of the occurrence of words. So for instance, cat is a very common word. So it would be something like 17. Sleeping is common, but let's say a little less common. So 24. And then let's say the cat is sleeping on the iPhone for some reason. I'm assuming this is a less common term, unless you guys can think of a even less common term. So that one for the BPE algorithm could be 2045. Do you see where I'm going with this? Like it'll create a list of terms, And then actually it gives the IDs based on frequency also. So it's a pretty complex algorithm. But once we have the set of IDs, then you no longer have this. You just have 17, comma, 24, comma, 2045. And the thus can be used. I just skipped them, but do you guys see what I'm saying? And then there would be about 40 of these, or the last ones are just masked out. Initially, just think of them as 0. Okay? So this is essentially what's happening. So this matrix, 32, comma 4, can hold these values, right? Because it would be, oops. It would be one row all the way to value 40. And then the next one would be another set of IDs all the way to 40. Do you see that? So that you would end up with 32, comma 4. So that's fine so far. But if you remember, I said that there's also a 512. So what does that mean? It means that we don't actually store the value 24. Instead, we have like a lookup table, right? That neural networks have. They have like a little lookup table. And so again, it's a rows and columns, right? That is going to be a matrix of size, vocabulary by embedding value. So embed, let's call it embed. So vocabulary, usually you'll be surprised, it's about 50,000. So 50,000 is usually the vocabulary size, okay? And then comma, I shouldn't have used this. And then this is the 512 that I was talking about. So what that means is that instead of representing a word as just the value 24, it is represented as what? As a vector with 512 values. If I say 512. If I say 256, 256 values. And that's similar to what I was doing before, playing with that projection. And then what about 17? 17 will have its own vector of size what? 512. And what about ID 2045? That's not going to be meaningful to a transformer. What it's meaningful is that it has its corresponding vector of size 512. Initially, as you will see me, I'll create it as just a random tensor, but during training, the values become updated. That's the intelligence of the AI model. To do that kind of training, you do need all the books in the world and all the internet, all the text in the internet. Got it? Does this make sense? The intuition, where it's coming? Any questions? Yeah, please go ahead. For each word? Because that's a good question. So think of it as an embedding space where every word is a point. So I'm creating an embedding space with 512 dimensions, and now every word is put in that space. So why is that valuable? Well, because you're learning how to put those points based on everything that you're reading. So maybe you're reading a lot about Washington, D.C., and USA. So, right? And then you're reading about Beijing in China. And so in that space, as the model is learning, it might learn that, okay, whenever I see China, I see Beijing over here. So if I see USA here, guess where I should look for Washington, D.C.? Over here. Do you see how it's capturing geometrically, if you want to think about it that way, the information of the text in this space? Go ahead. The dimensions, yeah. So so our space here is a three-dimensional space, right? And so all of us are points in it, right? And so we could say, like our coordinate, I'm like this coordinate and that coordinate, and I'm not up there, so I'm here. So those values define my position. But I could reorganize things based on other values. So we say like, I think we did this example last week. Instead of position, I say age, height, you know, weight, something like that, right? And so I can then organize all of you in this space based on that. Exactly. It's just instead of we can only visualize three, here we would have 512, but it could be 256, 718, whatever you want it to be. Sure. Yeah. I mean, 512, and that's the thing. You don't know what the large language model is going to do because all it does is it looks at the correlation of words. Remember, in LLMs, it's not even about like classifying is this a happy sentence or a sad sentence. It's really all it's looking at is the text. So it sees the cat is, so it pays attention to cat and sleeping, bank pays attention to river or place where you keep cash, right? So that's what it's the correlation of the words, but it's capturing that correlation in this embedding space of 512. Yes, exactly. Every word has to be. So like that's something that in the past, that embedding space was outside. So we would do the embedding space outside, and then everyone had a vector of 512 and it went into the neural net. What's the problem with that? Usually the word bank had only one embedding of 512. But now the LLM can give context. So it's seeing whenever you give it a sentence that says bank and the robbers took the money, like it triggers in its head a level of understanding because in that space, it's somewhere here with buildings and cities and things like that. But when it sees the context of a sandy bank of the river and fishermen or something, okay, that word bank immediately goes to some other part of that space where, it's like rivers. I don't know, maybe it has something to do with crime and finding people in rivers, something like that. My point is, see, it can make that connection better because it's closer to that. And that's only one of the parts that's going on. But some people have described large language models as just gigantic embedding machines. So a lot of its power, that's what the outcome that's coming, that you're getting. But the attention and everything in the architecture is being used during inference. So it's not just used for training, it's being used in inference. And that embedding is inside the network. So the learning of all those 512 happens inside the network, as we will see later. Make sense? Yeah, great. So right now I'm just creating it kind of random, right? So I can show you the matrix multiplications, and we're going to see how the data then, we perform more operations, the attention operation, and so on, until we get to the output. So my goal for today is to do this from in inference mode from input to output, okay? Without training, all random data, just so that we see the architecture. Later on, we can train the model and it should be pretty straightforward. Any other questions? All right, great. So I think we take a break at 6:20. So let me just finish this part here. All right. All right, so I'm doing the X. That is literally the input, right? Except that this input is not as fun, as easy as Iris, which was only 2-dimensional. This one is 3-dimensional. That's the only thing. And we have to do, but there's a couple of things that happen and then we get here, right? But this is a good starting point. Later in, with time, we will see the other part of the process. The only thing we may not cover is BP, that tick token, because that's pretty involved and it's kind of like goes in and out. So we'll see as time permits. All right, so let me do this one. And now, again, the key thing here is to look at shape. Guys. All right, we'll wrap up in a couple of minutes. So we do x dot shape, and you can see this is how you should always try to understand neural, guys. Yeah, this is how you should try to understand, everything that you're doing, right? So 32, 40, 512. When we run this through some layers of the neural net, you want to see the transformed version of it and so on. So essentially, when we give this, we'll give it 3240, but it will run it through one of these matrix multiplications and boom, it'll be 3240, 512. And there it is. All right. So we did that part. So that's going to be our starting point, our X. Okay. You can see that here. Now I'm going to do this whole attention thing, right? Which is somewhat complicated, but I'll break it down into parts. It should make sense. And essentially what we're doing is transformations, or a lot of people, before the term became transformation, it was called projection. So projection was really like the common terminology, but it's the same thing. So we use learned projection weights and biases to map the input embeddings into lower dimensional representations. And you'll see why. These are like tricks. This is actually like a relic of not very powerful GPUs. Okay, so they were kind of and by the way, the architecture that I'm following here is just from the 2017 paper, so the original paper. Okay, but a lot of the decisions they made then were just based on the limits that they had, and it was Google at the time. All right, so the next thing we will do is take a look at this, all right, so that we can start looking at the attention mechanism. Okay, so let me add a few code blocks. All right, and so what I will do is I'll just break this into the parts. So we will, whenever you talk about attention, you hear KQV, queries, keys, and values, right? So I'm sticking with the terminology, and I'll just show you the operations, essentially. All right, so it's 6:20 right now. Let's take a 10-minute break. We'll start at 6:30 again and try to finish this up all the way